Hello and welcome to another Quant Questions. I can tell by the channel I've been away for a good time now, and the reason for that is, well, there's two reasons actually. Firstly, I've been finishing my postgraduate degree off, my masters, and secondly, I've actually got a job. Now I'm working in as a quant analyst. So if anything, this is a great channel to sort of come to see for these sort of videos. So today I have obviously the three questions and the solutions that are standard on this channel. I'll be going through any questions about either any of the problems I do in this video or just being the job of a quant in general. Please put them in the comments below, and I'll try and get back to you within 48 hours of you putting them down. And like always, please enjoy this video. Thank you. Okay, so the first question, you're presented with the following gamble. You flip 100 fair coins. If 60 or more land on heads, you win £10. Very good. However, you win nothing on all other outcomes. Should you play this game for £1? Okay, so this seems like a pretty standard stats question, but here there's a bit of a trick towards the end, which you can really use to help you out on questions like this or similar. Okay, so first, so we've got here, say the n equals 100, so the trials, let's say, and then obviously a probability is a fair coin, so p is going to be 0.5. Okay, so normally this will be something like a binomial distribution, where we have np. However, because n is large, actually we'll do this at lowercase m, because n is large, we can use obviously the central limit theorem. So let's do write that as y, which is going to be a prox. Let's do a prox there, and it's going to be a null distribution by the central limit theorem. So this is np, and then we'll do np1 minus p, and that is just the formula for it. So what do these values equal? We have n times p, which is obviously just 100 times a half, times a half, which is equal to 50, and then for this one we have np times 1 minus p, so we can use the 50 from here, and then 1 minus p is just going to be 0.5, and so we have 25, or we can write this down as the standard deviation, which is just 5 squared. So now let's write it in this form. So we have y approx normal, 50 and 5 squared. Okay, very good. So we can write this out as a normal distribution. So we do line at the bottom, and I'm very bad at drawing, so it's going to be yeah, I'll give that one more go, and that's probably the best you're going to get. So let's just fill this in. We've got the mean, which is 50. Standard deviation is 5 squared. However, I'm not going to do that quite yet because we need to work out what the value of the expected value of the gamble. Now, clearly, we need this to be positive in order to play this game. So, firstly, we need to do the price of the game, which is minus a half. So we'll do minus a half, and then we need to do we need to do the probability of winning, and then the probability of a loss. So winning, we win £10 this game, so do 10, and then obviously this is just the probability of winning, which we haven't worked out yet, but that's the sort of the main root of the question. And the probability of loss, if we lose, we don't have to pay anything because we already paid £1 for the entry of the game, so we don't. So it's 0 there with the probability of loss. Ooh, loss. But obviously that doesn't matter. Now we obviously need this to be positive in order for us to play the game. Okay, so let's just rewrite this. Minus 1 plus 10 times the probability of winning. And obviously, square bracket there. And obviously we need it to be positive like before. Okay, so what is this? The probability of winning. So clearly we need to work out the probability of it being the probability of y to be greater than 60. So the heads, the value of heads there. So what is this? Now here's where the trick comes in handy. So to answer this sort of question, let's go back, or let's just redraw our distribution. Do that and do a different color. Have another look at this. Oh, that's not too bad. Okay, a bit skewed, but oh well. So we know that our mean is 50. Now here's the trick. So the trick is 95% of a normal distribution's mass lies within 2 standard deviations of the mean. So what does this sort of entail? We know that 1 standard deviation is 5. That's why I've written it like this. So 2 standard deviations. One standard deviation is equal to 5. So 2 is just going to be 10, which is 5 times 2. Okay, so this is where we do another dotted line like that. So this is going to be 60, and then the other side, we try and be as symmetrical as possible. It's going to be 40. So what does this mean? So this means that, let's just highlight this actually, 95% of this distribution's mass is going to lie within here. Approximately, that is, approximately. It's not exact, but it's approximately. It's very, very close. So that means 5% is going to lie outside. So we have 2.5% here and 2.5% here. And the question actually says, asks for greater than 60. So we know that it has to be around 2.5%. Now, you can see here that these values are chosen, or the values in the question are chosen to try and push you into this trick. And I say it is a very, very handy trick for questions like this and similar. So we know it's about 2.5. So we can now write the probability of winning is about 2.5%. So now let's put this back into the expected value of the gamble. Let's do the expected value of the gamble, which is -1 plus 10 times this one here, which is going to be 0.025. So it's going to be -1 plus 0.25, which is going to be negative 0.75. So should you play this game? Absolutely not, no, because you're going to have a expected loss if you play this game for £1. And now another part of this question is, it's not asked, but let's just do it. Let's just work out the value, the fair value of how much you should pay for this game in order to sort of break even or be risk neutral game. Now this is going to be obviously very simple. Expected gamble is just going to be, let's do the price of which is fair, and it's going to be minus the 2.5, and clearly we get that the fair value is going to be about 25p to play this game. So if you're ever at a carnival or any sort of game, and this game comes across, 25p is the value that you should play in order for this to work out. Okay, so the next question, a bag contains n socks, some of which are black and some of which are red. If 2 random socks are picked, the probability that they're both red is 1/2, which is nice to know. What is the smallest possible value of m for which this is possible? Okay, so let's actually define some notation here. So firstly, we're going to do, let's let Ri denote a red sock on ith pick. So for example, all this means is R1 is a red sock was picked first out of this bag. R2 means a red sock was, I'm going to do this to make it quicker, a red sock was picked second, that should be 1 there. Second, and so on, so you get a gist. So let's just draw this bag out. So we've got n socks, some of which are black and some of which are red, like follows. They don't have to obviously all be equal, but that is just how it looks so far. Now we're also going to let R be the number of red socks in the bag n. Okay, so what does this mean? So essentially we're looking for the probability of firstly picking R1 and then picking R2, and we know that this is equal to a half. So we can rewrite this as probability of picking red sock, and also the probability of picking a second red sock, given that we've just picked a first red sock, and we know that this is equal to half. So we can write this in more compact notation. So this is R over N times second choice, which would be R minus 1 over N minus 1, and we know this again is equal to a half. So one way to do this is just literally trial and error. So clearly N equals 1 just wouldn't work because you need to pick 2 socks, so we need the bag to be a bit larger. Again, N equals 2. If N is equal to 2, then this can't hold because we absolutely have 2 red socks with 100% probability, and we know that probability has to equal a half. So again, this wouldn't work. Okay, so let's now try N equals 3. So we have what we have. We have R over 3 times R minus 1 over 2, and then we know that this is equal to a half. So let's take this. Let's take this product here of 6 and times it by here. So we have R minus 1 equals 3. I know that there's no integer values that make this true because 2 minus 1 is not equal to 3. Yeah, so we know that there's no integer values for this to be true. Finally, let's try N equals 4, and we should see a better result here. So R over 4 times R minus 1 over 3 equals a half. Take this product, times it here. So we have R minus 1 over, or equal to 6. And finally, we know that if R is 3, then this would be 3 times 2, which is indeed equal to 6. And so the smallest value we need is for N to be equal to 4, and where R is equal to 3. And that is that question solved. Okay, so now I've moved over to my laptop because we're going to do a programming question now. So I'm going to move my camera down and you should be able to see the question. Okay, I think that should be good enough. Yeah, that'll do. Okay, so the question is, write a function, a Python function, to check whether 2 strings are anagrams. Write a version that uses sorting and a version that does not use sorting. So, for those who don't know what an anagram it's say you have 2 words, you can rearrange them to make the different word of that. So, for example, I should have come up with one example before I start recording this, but here's an example on the screen now. But okay, so let's first do the version that uses sorting. So this is quite simple in Python. So we're going to create a function. I'm going to check, call it is anagram. So I'm going to take in 2 strings. Let's call it string 1 and string 2. And then we're just going to do the, the first check is to check it is the same length, because the 2 anagrams have to be the same length. So let's just do a check for that first, because if not, we can just output false straight away. So is string 1 is not equal to the length of I'm using the different keyboards as normal, so the typing's a little bit off. So the length is not equal to the length of string 2, we're going to return false straight away. And then if not, we're just going to do return the sorted using the inbuilt Python sorted. Now this will just arrange the characters in alphabetical order, and then so we're going to compare we're going to take the sorted list of string 1, sorted list of string 2, and then if they're anagrams, they should be able to be exactly equal. So string 1, we're going to check if it's the same as the sorted of string 2. Now this should work. I'm just going to actually initialize 2 strings. I'll just do it in one line. String 2. And let's just use, I could have used the example that was on screen before, but I'm going to use QWERTY, and I'm going to go the reverse of that because it's easy on the keyboard. So initialize the 2 strings, and then we're going to check The sorted version is anagram. That should autocomplete. It's going to autocomplete. It's taking a while. Ooh, have I put? Nope. There you go. This is string 1 and string 2. Now they should say true, which it does. Let's double check this is right. I'm going to first check the length, so that this should be quite quick because it's going to take the first if statement. Straight away false, and then let's put in an extra letter which is the same length but just is not equal, and that should also do false, which it does. I'm just going to change this back just so we can use this. Okay, so that is the sorted version done. Let's go now on to the unsorted. So the idea here is we're going to have an array that has the numbers from 0 to 25 because of 26 letters in the alphabet. We are assuming that these are all lowercase values. So yeah, we're going to assign a value to each number. We can do that with the Python function ord. And then from here, we're just going to have another array of all zeros. And then what we can do with this is check each character and then increase the value of value of that in the all zeros array. And then on the second string, we can take them away, and then this array should be equal to 0 if they're all true, because they'll cancel each other out. Now that will not make sense. However, if I get going, I'll try and describe it as we're going along. So firstly, we're going to need to have the function that turns the letters to a number. So we're going to do letter to num, and this is just going to take in a letter, obviously. So we're going to do straight away return ord of letter. Now this just assigns the value to the characters. I think ord A is just 97, I believe. Let's have a look. It is 97, yeah. So it just uses the basic ASCII. Now what we're going to do is assign it from 0 to 25. So we need to take away the ord of A, because that will make sure A is 0 then. So let's just double check that. So letter to num. Now this should be 0. Beautiful, it is. And then Z should be 25, which it is. Okay, beautiful. So let's get rid of that. So next we're going to have to actually do the actual function. So we're going to do is anagram, can't spell, on usort. Just do usort for unsorted. If I take in the string 1 and the string 2 again, and then here we're going to do exactly the same before to check the length. I'll just copy this down. There's no point in rewriting what I've already done. So check the length, and then here's where we're going to assign the array. So this is going to be a list concatenation, just because why not? So from 0 for I in range 26. So this is going to output letter count is going to be an array of all zeros from 0 to 25, because obviously we start at 0 in Python. Okay, so next we need to check for letter in string 1. Letter in string 1, yeah, that's right. So we need to increase it for each letter. So the letter count is going to take the value of letter to num. So when that loads, yeah, and then we're just going to input the letter, and then on this we're going to basically increase it by 1. So we should have. So this function, this array here will be increased by each letter. So then we do something slightly different for the next one. So letter in string 2, and then we're just going to take it away here. Letter count, letter to num, and then we're just going to do the same again, but like I said before, just take it away by 1. So this should mean that if the letters are the same, or if it is an anagram, the final letters count should all be equal to 0, because one is going to increase it, the other is going to decrease it. And then if there's values that aren't equal to 0, we know that it cannot be an anagram. So So let's just do that now for count, or for count in letter count. If count does not equal 0, we're just going to return. Right, nope, I've missed that, so this needs to be shifted over. Take that away. It's going to be false, and then obviously we can return the alternative false. It should be an anagram. Let's check there's no compile errors or no syntax errors. No. So let's now try this. Is anagram you thought? I'm just going to input our string 1 and our string 2 from before. Output this. Ooh, string 1, string is false. Why is that true? Have I don't think I ran a new version of this. So let's just put that there. Should be true now, which it is. Beautiful. Let's do the same as before. Let's take away a letter. It should be false. Beautiful. And now let's add a random letter H. And it's false. Beautiful. Okay, so that is the programmer side of the quant questions done. So if you enjoyed this video, please leave a like, and like I said before, comment anything, and I'll try and help you out where I best can, or put you in the right direction. And if you've got any more sort of ideas of videos I can do, again, put them in. I think I'm going to just carry on this sort of series now, the quant questions, because my last one seemed to do pretty well. So yeah, and thanks for watching.